Uh, I'm İlim İrfan Çimdiker, and right now I'm a PhD candidate studying cosmology group in Poland and a visiting researcher in University of Bologna. So basically, I was a master's student of Durmuş Demir. He was like a mentor to me, and as you all know, he was a epitome of hardworking person. He was a really, really good particle physicist, and we worked with him for 2 years, and mainly on his theory of emergent gravity. So, of course, I want to dedicate my talk to him. So today I will talk about, I'm mainly working on phenomenology of black hole thermodynamics and non-extensive entropies. As you know, black holes are enigmatic object. I will be quick. I will not extend my talk. So basically they are enigmatic objects, and basically they need to be simple because you can parameterize classically a black hole with three parameters. I mean, mass, angular momentum, and electric charge. However, they shouldn't be that simple because let's say if they don't have an entropy, you could violate the second law in the universe. So as you all know, maybe in 72 and 73, Bekenstein showed that, okay, we have an entropy related with the horizon area of the black hole. And later Hawking showed that in 74, black hole emits a thermal radiation inversely related to their mass for Schwarzschild case, but related to their surface gravity. These are semi-classical considerations, as you can see from the H bar there in red. So I will just focus on Schwarzschild case in my talk, where we have the surface gravity inversely proportional to mass, as you see. So the thermodynamics of black holes are really analogous to the classical thermodynamics. We have first four laws, and we have a transitivity law, that is the zeroth law. And the first law is the rewritten form of the energy conservation, as you can see. The second law is that you are tying the area to the entropy, the classical entropy. The area is strictly increasing with time. And third law is it is impossible to reach zero temperature in a physical process, but the third law is a little bit shaky because some external black hole breaks that. However, I will not go into details right now. Some peculiarities about black hole thermodynamics. Peculiarities here, I mean that your regular black hole thermodynamics is different than classical thermodynamics because, I mean, there are some main differences between them, as you expect. So one of them is that we don't know what are the microstates of the black hole entropy. Okay, there you can came up with many ideas that why we don't have such a thing, but when you look into that, basically, you can. I mean, the main reason seems to be that your density of states in black holes is basically proportional to the exponential of energy square. And as you know, for classical thermodynamics and in QFT too, in order to be write down the partition function, your density of states should scale with the exponential of energy. And why is that? In basic terms, you want your internal energies to be additive, basically your Hamiltonians to be additive. But in the black hole, it's not the case. And again, I'm talking for Schwarzschild black holes. We have unstable black holes. I mean, we have negative heat capacities for the black holes. Again, why do we have that? It's not surprising because in long-range interacting systems, we already have, for some large-scale structures, negative heat capacities and unstable thermodynamics. And one thing about the Hawking radiation itself is that it is really sparse. What do I mean by sparse? The time it takes between each successive particles to radiate is extremely large. This also means that your thermal wavelength of your radiation is comparable to the body itself. So these are peculiarities, but in a basic sense, why this is happening? Because the black hole entropy or black hole thermodynamics are not like regular thermodynamics is an extensive quantity. What do I mean by that? So in regular thermodynamics, the entropy is an extensive quantity. Basically, if you write down one of your thermodynamic variable in terms of others, and if you want to scale one of your thermodynamic variable, all thermodynamic variables should scale with the same value if they are extensive variables. In, for example, regular thermodynamics, you can write down S as a function of U, V, and N, internal energy, volume, and number of particles. And if you scale these thermodynamic variables with A, your entropy will be also scaled with A. This means that your entropy is a first-order homogeneous function of your thermodynamic variables. However, black hole thermodynamics do not have this structure. So beyond extensivity, what do we mean by that? Why do we have this structure in regular thermodynamics? It is easy because basically when we think about our subsystems, we see that, okay, we have a subsystem, they can be interacting, but we assume one thing, and that one thing is that we assume short-range interactions. Short-range interaction means that, okay, if you have your subsystems, only interaction can happen at the area contacting the subsystems. So basically, when you go to the thermodynamic limit, your internal energy of the subsystem will scale with the volume. However, the interaction energy with this will scale with the area. So in thermodynamic limit, you can, okay, let go of the interaction energy. However, if your interaction term contains long-range interactions, then your thermodynamic variables may start to depend on the shape of the system. Let's look at from the probabilistic sense. What I'm saying is that for a short-range interaction, think like a spin system. For example, if you have a spin up and down, you have two states, you have C equal 2, and N is your particle number. When you take the logarithm of this, you will get an entropy scaling with the number of particle N. So basically, when you add two systems, N plus N will be constant, so that your entropy will be an extensive quantity. However, not every system needs to follow this exponentially tailed distribution. We have, in some part of physics, power law distributions and many other distributions as well. So in order to write down an entropy for these kind of things, you need to basically generalize the entropy you have. So as an example, and to be concise, basically I try to work on black hole thermodynamics with all the entropies here, but I will focus on one thing as an example here. So let's focus on Salish-Q and Rényi entropies here and give an example about that. For example, Salish-Q is a one parameter generalization of the Gibbs entropy. It's also known as Q entropy. The term here is that it is called as Q logarithm. In mathematics, we have Q generalized algebra, and this is the one form of the Q logarithm. And now you can see that instead of your entropy scaling with pi, it scales with pi to the power q. So it has a power law distribution. However, one peculiarity with this is that your composition law of the subsystem changes. And in basic thermodynamics, you know that entropy of the subsystems should be additive. However, if we break this, if we generalize the entropy, your subsystems do not need to be additive. And for black holes too, we observe this, right? You cannot write the additive subsystem composition rule for the black holes. Anyway, in 2000s, Abe came up with the idea is that, okay, what can we do with this non-additive composition rule? He came up with the idea that, okay, I can write another entropy by modifying the composition rule to an additive form, and then I can use a Clausius relation on them so that I will have two entropic systems, but they will yield the same physics. And for this case, the Rényi entropy, you may know from the information theory, you can write down a form of SQ here, as you can see. And basically, you can write a function of SQ, and if you minimize this, you will get the same temperature, physical temperature of the Q generalized entropy. So they are basically related to each other. So basically, if we write, let's now look at this Rényi entropic form and what Q does on the system. This is a random variable, two random variables. As you can see that the black one, H1, is Gibbs entropy. You can think that, okay, a spin system with up and down with two particles. You may remember from the textbooks, especially this one. So as you can see, introducing Q, dependent on the value of Q, basically you introduce a bias to your system. What do I mean by bias? Depending on the value of Q, you make likely events more likely or unlikely events more likely. So basically, I just gave some values of here, H0, H1, H2, and H infinity. These are some limits of Rényi entropy, namely mean entropy, Gibbs entropy, collision entropy, and max entropy. However, Q is a free parameter in Salish-Q entropy, so it can take value, any positive real value. So what does this do for the black holes? Okay, this is in the literature known as Rényi black hole. And as you can see, this black one, which is the Q equals 1 limit, is the Schwarzschild thermodynamic variables. You have an exponential increase in the entropy. However, when you introduce a little bit non-extensivity into the system, entropy starts to scale with the logarithm of the black hole area. And in the temperature, you can see that we have a Hawking page-like transition, basically. So for large black holes, temperature tends to increase. And from the heat capacity, you can also see that we have a phase transition, a discontinuity here. So we have, for large black holes, we have positive heat capacity and stable black holes. And in here, you can also see that sparsity for black hole is large, and when you introduce a little bit non-extensivity, basically your sparsity goes down. Sparsity goes down means that it starts to behave more like a classical black body object. So basically, I would try to give a basic example of what I have worked for now. And what I've done so far is that, okay, I worked on mainly non-extensive thermodynamics. We have generalized this Abe's work of these relations between two entropies and said that, okay, you can write down for any non-extensive entropy an equivalent entropy and came up to the same physics. And I've analyzed the various non-extensive entropies with generalized uncertainty principle. You can, if you are interested, you can read this. And right now what I'm working, as I'm a cosmologist, I'm trying to work on holographic dark energy models with these various non-extensive entropies. You can see that here is that dark energy is dynamical. This is dark energy. And it depends on the area of the future event horizon. What would happen if these entropies modify the area so that what would happen to our dark energy, basically. So thank you for listening. Again, thank you.
So we have a coffee break. Simple question.
Thank you.
If you go back to the chart where you showed different, yes, this one. From statistical mechanics point of view, I understand the horizontal one, the maximum entropy. So when you say, for example, H infinity,
yes,
minimum entropy, that is the most ordered state.
Yes.
So what does it mean for the black hole system?
It means, okay. For a black hole system, H infinity doesn't mean anything. Because from informational point of view, I think it was related to the number of, some proportional to the number of possible states. So I mean, but for a black hole, if you introduce a non-extensivity, Q needs to be near in the order of 1. Because this needs, I mean, the temperature needs to have a correction term. But H infinity, I don't know, it will be hypothetically related to the number of states in your system.
And how about H2, for example?
H2, again, is a collision entropy. It's in the, again, in the information theory. So if you introduce 2, I mean, larger than 1 or really smaller than 1 entropy, I mean, values, you get non-physical events, I would say. So what we need is that Q needs to be in the order of 1, unfortunately, and it needs to be small. Because as you can see in black holes too, I mean, black hole pictures too, I mean, these resembles ADS-like structure for the black hole. So you can relate these, basically they are exactly like ADS black holes. You can relate them. So in a physical sense, Q needs to be in the order of 1. So thank you.